Tēnā koutou, katoa, ngā mihi nui, he mihi mahana ki a koutou. Welcome and thank you for coming along to our virtual science talk. My name is Dr. Ben Payne and I work here at East Coast Lab. Here at East Coast Lab, we want to make it easy to learn more about natural hazards and how they affect us. Tonight we'll learn more about the science underway a short distance from our coast on the Hikurangi Subduction Zone. Some of you may already know this, but the Hikurangi Subduction Zone is New Zealand's largest and most active fault. We will hear from two leading New Zealand scientists. They might not like me to say that, but their work is certainly well respected internationally. And firstly, I'd like to introduce you all to Kate Clark, who is a paleoecologist and earthquake geologist at GNS Science, and Dr. Laura Wallace, who is a geophysicist at GNS Science. Both Kate and Laura are studying the subduction zone as part of a 5-year Endeavour research program funded by the Ministry of Business, Innovation and Employment. I would also like to introduce you to my lovely colleague, Natasha Blunden. Natasha is the project leader at the Hikurangi Response Planning project, which is kind of putting all of the science that people like Laura and Kate are doing into practice as we plan and prepare along the East Coast region. Just before we get underway, a little bit of info on how this will work. Natasha, Kate and Laura will run through a presentation first. This covers some fascinating material on from their work. And then after the presentation, I'll facilitate asking the panel of presenters some questions from our viewers. So if you have some questions, those burning things you want to ask the scientists, please write them in the chat box on Facebook Live. And we'll be keeping an eye on these for question time at the end. Anyway, without further ado, we'll move to Natasha, who's going to cover off on the Hikurangi Response Planning project.
Hi everyone, as Ben said, my name is Natasha Blunden and I'm the project leader for Hikurangi Response Planning out of East Coast Life at the Boundary. So before we move on much further, first I want to explain to you a little bit about what's happening in the North Island. So in the North Island, we have the Hikurangi Subduction Zone, and the Hikurangi Subduction Zone is actually New Zealand's largest and most active fault, and that's where we have the Australian plate meeting the Pacific plate, and where they meet, the Pacific plate is diving westward below the Australian plate. So where these two plates meet, we have a fault, and like all other faults, this fault can produce earthquakes, both large and small. And when we have earthquakes on the subduction zone that displace the seafloor, so when the seafloor moves up or down, we can also get tsunamis. So we know that subduction zones are known to produce the largest earthquakes and tsunamis in the world. And many of you might remember a few events that have happened in the past. A few examples include the 2011 Japanese earthquake and tsunami, and also the 2004 Boxing Day event, which was a magnitude 9.3 earthquake and tsunami. And we know that the Hikurangi subduction zone could produce a similar size event. So that's why it's important that all of us take action to plan and prepare for this risk. And when I say all of us, that means myself, that means yourselves listening tonight and your families, but also the businesses and organisations that you work for. And it's really simple and easy to get prepared. We can practice our tsunami evacuation route. We can make a household plan, could be with our flatmates or our family. And we can make sure we have a go bag ready at home and in the office in case something happens. And because we know that the impacts of a Hikurangi event would span wider than one region, this is an event that would affect all of New Zealand, the Hikurangi Response Planning project has been collaborating with scientists, emergency planners and lifeline organisations such as NZTA, gas and power companies, to plan for this risk in the lower half of the North Island. And we've been working together over the last 2 years or so, and one of the main outcomes from this project is the guidance on the left that you'll see, which is the response planning toolbox, which will be coming out in July this year. So as you might have noticed, emergency managers, we do rely on science when we're planning. And over the last 2 years, we've heavily relied on science about the Hikurangi subduction zone, because it's important that we understand how the subduction zone has behaved in the past, because this gives us clues as to how a future event might impact New Zealand. And when we know what the impacts might be, we can plan for those, and that might be response planning, but it might also be taking action right now today and identifying things that we can do to increase our resilience. So before I move on and hand it over to Kate, I just want to make a quick note that although we talk a lot about big earthquakes on the subduction zone can experience both large and small earthquakes, so it's important to keep that in mind. So I'll hand over to Kate now.
Kate, you're on mute. Why is it? I don't know how we. Sorry. Unmute audio. I don't know why I had you on mute.
Am I still, can you hear me now?
Perfect. Sorry.
Thanks, Ben. All right. Tēnā koutou katoa. Thank you for joining us this evening. My name is Kate Clark. I'm an earthquake geologist at GNS Science. And I'll just head back one slide. Okay, so tonight I'll be talking about how we understand the likelihood of a large earthquake on the Hikurangi subduction zone by using information about what the subduction zone has done in the past. So our research at GNS Science has shown that the Hikurangi subduction zone has produced very large earthquakes and tsunamis in the past. And I'm going to talk about 3 topics that help us understand what will happen in the future. So we can look at 3 areas. One is comparing the Hikurangi to global subduction zones. The other is looking at our historical earthquake record. And the one that I'll spend the most time on is looking at our geological history of large earthquakes on the Hikurangi subduction zone. Okay. So when we look at our Pacific neighbours everywhere, sorry, there's a delay in changing slides. Oh. Okay, so this slide shows recent large earthquakes around the Pacific Rim. So when we look around the Pacific Ocean, there are lots and lots of other subduction zones. And most of these subduction zones have experienced very large earthquakes in recent times. So Natasha mentioned a couple, the 2011 Tohoku earthquake and tsunami up in Japan, the Indian Ocean tsunami in 2004, the 1960 Chile tsunami and earthquake in 9.3. These are examples of very large subduction earthquakes. So most of our Pacific Rim neighbours have experienced these very large earthquakes, and we're kind of an anomaly down here in the South Pacific. We haven't seen anything very large in our sort of recent past. This next slide, when it arrives, will show, sorry about the delay. Okay, well, the next slide, when it comes.
It says you're controlling it, Kate.
Yeah, I'm pressing advance. It's not doing anything. Maybe it's better if, okay, now it's changed.
That's so weird.
I think there's a big delay. Maybe it's better if you control it, sorry. So historic earthquakes on the Hikurangi subduction zone, there haven't been any really large earthquakes. So I'm sure most people can think of some large earthquakes like the 1931 Hawke's Bay, the 2016 Kaikoura earthquake. These did occur along the Hikurangi margin, but these were on fault lines in the overlying Australian plate. So the particular earthquakes that we are studying and concerned about are earthquakes, large earthquakes that occur on the boundary beneath the North Island, that boundary between the Australian plate and the Pacific plate. So in our sort of recent history, so since sort of written records and in our period of instrumental monitoring, the largest earthquake we've had is the 1947 magnitude 7.2 earthquake up in Poverty Bay. So this is not, it wasn't a very particularly large earthquake. It did produce quite a large tsunami up to 10, 11 meters along that part of the coastline. There are hints of large earthquakes and tsunamis that occurred around about the 15th century from Maori oral histories. It's hard to decipher if these were, if this was one very large earthquake on the subduction zone or a series of smaller earthquakes, and if it did occur on the subduction zone or not. So to really understand the sort of the likelihood, we need to understand the frequency of large earthquakes in the past. So to do this along our Hikurangi subduction zone, we mostly rely upon the geological history of these large earthquakes. So even though these earthquakes, the rupture zone is far beneath our feet and often most of it is offshore, it does leave a mark along our coastline. So these great earthquakes leave geological evidence, and what we have in between earthquakes is parts of the coastline going up and parts going down. And then during an earthquake, you can get very sudden movements that permanently lift up some of the land, and some of the land subsides. So parts of the coastline will go up and parts go down. And when that earthquake occurs, you can also get a tsunami generated. So these are the three types of geological evidence that we look for along the east coast of the northern South Island and right along the east coast of the North Island. This next slide, so this shows examples of where we see coastal uplift, coastal subsidence, and tsunami deposits. So great earthquakes, when they uplift the land, what we end up with is sort of a step along the coastline. So these are what we call marine terraces, and you can see some really nice steps in that coastline under uplift there. Some examples from up near Gisborne, Mahia Peninsula in the middle there, and along the Wairarapa coast down the bottom. So these are where beaches have been uplifted and abandoned by the sea because the earthquake thrust them out of the water. Subsidence, we usually record subsidence in parts of our coastline that host large areas of low-lying wetlands and lagoons. So there's examples there of lagoons up near Wairoa, just south of Gisborne, and lagoons down in the northeastern South Island near Blenheim in that middle photo. So these are areas that we can go to find evidence of when the land has dropped suddenly in large earthquakes. And on the other side of the screen, there are examples of tsunami deposits. So when large tsunamis occur, they can pick up lots of sediment from the offshore marine environment and from the beaches, and then it deposits these on land in the terrestrial environment. So we can look for these sand layers that give us clues about past large tsunamis. So this next slide should be coming. This shows an example of where we've looked at lagoons for evidence of subsidence and tsunamis. So this is an example from that area in eastern Melbourne near Blenheim. We tend to go to these nice salt marsh areas. And in these salt marsh areas, we take cores, so just using hand cores that only go in this area a metre or a metre and a half deep. So this extracts the sediment that underlies those salt marshes. And we look at these little tiny microfossils called foraminifera, and they give us a history of what the sea level has done at that site through time. So they're very sensitive to different sea levels, and they can tell us with precision of centimetres to tens of centimetres what sort of the tide level was at various stages through the past. So if they suddenly change from a high tide environment to low tide, we can tell that there was a sudden change because of land uplift or subsidence. And we can combine that with looking for evidence of tsunami sands. And we also, what's really important for us is once we've identified an earthquake or sudden movement of the coastline is to radiocarbon date that and determine the age of that earthquake. So we search for little bits of organic matter in these cores, so things like twigs or seeds or shells that we can radiocarbon date that tell us about the timing of these past earthquakes. This next slide will show us the next slide will show us an example of coastal uplift. Okay, here it is. So this is an example of where we've studied uplift to give us clues about the timing and size of past earthquakes. This is along the Wairarapa coast, where at this site we excavated a trench that went right across several of these steps of abandoned beaches along this coastline. When we do this, we dig the cover sediment on the terrace right down to the abandoned beach platform. And then we take shells that were living on these beaches at the time of the earthquake that were killed by the earthquake, and we radiocarbon date these shells and we measure the elevation of them above sea level. So this tells us about the amount of uplift that occurred in an earthquake, and it tells us about the timing of that past earthquake. So when we put all of this information together, it gives us a sort of timeline of when past large earthquakes occurred. So we put together lots and lots of sites from along the Hikurangi margin to understand when these really large earthquakes occurred, because you see evidence for them at multiple sites. And this just shows different areas of the Hikurangi margin that have had earthquakes in the past, and along the bottom we can see the timeline of when these large earthquakes occurred. So in total we see evidence for about 10 large earthquakes in the past 7,000 years. We think the last large subduction earthquake was about 500 years ago, and this mostly affected the southern part of the Hikurangi margin. And we can see that the time intervals between earthquakes vary quite a bit. So the smallest amount of time between large earthquakes has been about 350 years, and the largest interval of time has been about 1700 years. From the information that we have, we can't precisely calculate the size of these past earthquakes, but because they were large enough to leave geological evidence, they were almost certainly larger than magnitude 8. And I am going to hand now on to Laura Wallace to tell us about what's happening today on the Hikurangi margin.
Okay, great. So Ben, I have control of the screen now. Okay. Hi, I'm Laura Wallace. I'm at GNS Science. I'm a geophysicist. And so Kate's taken you guys into the past to try and understand what's happened on the Hikurangi subduction zone through the past. And I'm going to talk more about what we think is happening on the subduction zone right now. And one of the main tools that we use to try and figure out what the subduction zone is actually doing right now is Global Positioning System, GPS. We can actually use GPS to actually measure very tiny movements of the land, millimeter level movements of the land over time. And the reason that this can tell us a lot about the subduction zone is because when the two plates are coming together, the Pacific plate and the Australian plate, there's a lot of, on parts of the boundary, there's a lot of friction, sort of like sandpaper, and they're very, very resistant to slipping past each other in those places. And they can become stuck together sometimes for hundreds of years. And eventually enough stress builds up because of the sticking together of the plates that overcomes the strength of the fault, and the fault will slip in an earthquake. So it's this stress buildup phase, this locking together of the plates that we want to try and measure with GPS. And when this plate locking is occurring, it actually causes the crust around the plates where they're locked together to sort of distort and scrunch up. And we can actually measure that distortion and scrunching of the crust at the Earth's surface with GPS. And so this picture here on the left is the kind of image we've built up for what the Hikurangi subduction is doing right now in terms of where it's sticking together and where it's creeping from GPS really over the last 20 years or so. And so this is basically showing us a map view of the subduction plate boundary, kind of looking at it from above. This bit here out to the right of the figure is where it surfaces offshore, the east coast, where the two plates meet at the seabed. And then this bit down here is where the plate boundary is at about 70 kilometers deep beneath the central North Island. Just for reference, in Wellington, the plate boundary is at about 25 kilometers beneath our feet. And in Napier area, it's at about 15 kilometers beneath your feet. So what we see here is the blue colors are the area where the GPS is telling us that the plates aren't really sticking together too much. They're mostly creeping past each other steadily, whereas in the southern part of the North Island, we see a very different picture beneath the Wellington and the Wairarapa region. The two plates appear to be strongly stuck together, and we think they're probably building up a lot of stress that at some point in the future will eventually be relieved in an earthquake. So this is what's happening right now in terms of where the plates can slip past each other currently and where they're sort of sticking together that we can tell from the GPS. So let's see about this delay here in the slide flipping. I'm going to talk in the next slide a little bit about some of the other things that we can get at with GPS. Let's see if I don't want to jinx it and do it again, but I'll try clicking again.
It's such a pain.
Sorry, y'all. Technical difficulties of science. So in the next slide, once it comes up, I'm going to talk about these things called slow slip events or slow motion earthquakes. So a lot of you have probably heard of slow slip events or slow motion earthquakes. And what they are, they're really similar to an earthquake. That's why we call them slow motion earthquakes. You know, as many of you probably know, in an earthquake actually involves a sudden movement between two pieces of the Earth's crust, you know, sometimes a matter of meters of movement in seconds. And so you get that sudden seismic energy release and shaking. A slow motion earthquake also involves faster than normal movement between two pieces of the Earth's crust. Whoops. Thanks, Ben. Can you start that video?
It just hates me. I don't know quite what it's.
Can you just click on that black box there?
Yeah, I'm clicking on the black box, but it just.
Okay, so there's, if you go down to the bottom of the black box, there's a little control bar to play the video.
No.
Okay, we're not going to get the slow slip video. I'll give it to you with my hands. So if you go back to the slide.
Sorry, guys.
Okay. So getting back to what a slow slip event is you know, a slow slip event similar to an earthquake, except it's in slow motion. So in a slow motion earthquake, slow slip event, we get, you know, centimeters to tens of centimeters of movement along the Hikurangi subduction zone over a period of days to weeks and sometimes even years. And the reason that we know these are happening, we can't detect them with seismometers because the movement's too slow. You can't feel them. So the way that we know that they're happening is actually using GPS instruments on the surface. GeoNet operates in that upper right corner there. GeoNet operates a network of these continuously operating GPS that are running every day, 24 hours a day, 7 days a week. And they're able to detect small millimeter level movements of the land on a daily basis. So when these slow motion earthquakes happen, for example, this is showing data from about 10 years of data from a site near Gisborne on the East Coast. So when a slow motion earthquake happens in the North Island, we tend to see an abrupt eastward movement. So that's that upward movement on this plot here. This is one in about 2010. And the most recent one in Gisborne here was in 2019, the middle of last year, we had quite a large one. So these slow motion earthquakes really are ability to see that they're happening and that the Hikurangi subduction zone is constantly moving and constantly having these little silent earthquakes really hinges on our GPS monitoring capability with GeoNet. You know, and scientists really only found out that these things even existed, you know, really about 20 years ago. And that was because of GPS technology. And they've really opened up a lot of questions about how faults work and how earthquakes are generated. So let's try to go to the next slide. And so what I'm going to show you next, when we get to it, is where the slow motion earthquakes are happening beneath the North Island. So there we are, perfect. So what this map here is underneath is actually that map of the sticking, the locking, and the creeping that I showed you earlier. But overlain on that are these colored contours. And that's the areas where we've seen the slow slip events, the slow motion earthquakes in the GPS. And I'll focus in on two main areas of slow slip. One of our big slow slip areas is off the East Coast, so offshore Gisborne and Hawke's Bay, these red contours here. And these slow slip events are very shallow, probably happening at less than 10 kilometers depth on the plate boundary. You can see in this figure in the right here with all these dots, these what we call GPS time series. These are these big upward jumps are the slow slip events. And you can see here we have them fairly frequently off the East Coast, about every year or two. They're quite large, can involve 3 or 4 centimeters of movement over a period of a couple of weeks. And these events tend to be fairly short, maybe a few weeks, sometimes longer. But then we see a very different situation if we go down further to the south, to the Kapiti region, so west of Wellington, and the Manawatu region, the red contours down there. Down on the lower right are some examples of GPS data from that area. The top one is from Levin, and the one underneath is from Kapiti Island. What we see down here is a very different story. The slow slip events happening in that area are very deep on the subduction plate boundary. They're further west where the plate boundary is deeper, probably 30, 40 kilometers depth. And they have a very different behavior. They tend to be much longer lasting slow slip events, so lasting about a year or so. And they're also a lot less frequent. Down in the Kapiti and Manawatu area, we tend to see them about every 5 years, but they're also quite large. So a lot of these big slow slip events in New Zealand can cause 3 or 4 centimeters of displacement at the land surface. And to put that into context, that's about a year's worth of plate motion. So that's, up in the Gisborne area is happening in a couple of weeks. So it's really, much faster than normal plate motion when these things are happening. Okay, so one of the other key aspects of the slow slip events that makes it really important to try and study and monitor and know when they're happening is that in New Zealand, we often see swarms of earthquakes during slow slip events. In some cases, even earthquakes up to about magnitude 6. And we think that these earthquakes happening during the slow slip events are actually happening due to sort of changes in stress in the Earth's crust that's induced by the slow slip event itself. So the slow slip events, in many ways, they're actually really great because they're relieving a lot of that built up plate boundary tectonic plate motion stress where the slow slip events are happening, but they can also redistribute some of that stress onto other faults in the region and trigger small earthquakes to happen. There's also been some observations in other parts of the world. For example, prior to the magnitude 9 earthquake in Japan in 2011, there's good evidence that there was a large slow slip event leading up to that earthquake that may have actually triggered that earthquake. So that opens up the possibility that slow slip events could actually trigger larger earthquakes. However, I want to point out we haven't seen that very often. I think that's very rare, but it really makes it even more important to understand this relationship between slow slip events and earthquakes. And once we can really better understand how slow slip events can actually set off other earthquakes, then we might have a really good chance of improving our ability to do better forecasting of earthquakes. I don't think we'll ever be able to predict earthquakes, but I think we do have a good shot at doing a better job forecasting them. So the next one. So this slide, I really want to try and kind of bring things together a little bit from what Kate talked about and what in terms of the past earthquakes, what the Hikurangi subduction zone has done in the past, and then what we know it's currently doing right now in terms of this locking and these slow slip events. So we can actually bring all of this information together along with a lot of other observations and information that other scientists have been gathering on the Hikurangi subduction zone for many years. We can bring these together to really constrain seismic hazard models and tsunami hazard models. And we're really currently actually actively in the process of incorporating all of this new information that's been generated over the last few years to really improve how the Hikurangi subduction zone has been incorporated into these models. So that's going to really help us understand how the subduction zone contributes to seismic hazard and tsunami hazard in New Zealand, which is really the ultimate goal of a lot of the work that all of us are trying to do. So if we go to the next. Okay. Oopsie, did I do that or did Ben do that? Okay, so, and then I kind of want to wrap up a little bit. You know, a lot of you are probably aware of a lot of large earthquakes Kate mentioned and Natasha mentioned on subduction zones elsewhere in the world. And we've learned a lot of lessons from these earthquakes in the past. And one of the specific ones I'll bring in from the northern Japan earthquake, the magnitude 9 earthquake in 2011. This picture on the right here is a map of northern Japan, and these green contours are the part of the plate boundary that slipped or ruptured in that earthquake. If we take that part of the plate, the green contours, which is the area that moved, and we superimpose it on our Hikurangi subduction zone, you can see that we could easily host an earthquake of that size on the Hikurangi subduction zone. For example, if we ruptured beneath the southern part of the North Island and maybe into the Hawke's Bay region, where Kate, you know, in both areas, Kate sees a lot of good evidence for past earthquakes there. So we do think that there is potential for the Hikurangi subduction zone to produce a magnitude 9 earthquake. We don't know quite yet if it has actually done this in the past and if it's capable of doing that in the future. A lot of the work Kate's doing will shed a lot of light on that. But this is something we do actually really need to think about and be prepared for, and you know, really be prepared for events potentially like this in our planning in the future. And I just finally want to wrap up with, there's been a lot of aspects of these recent large earthquakes, such as those in Japan in 2011 and the Indian Ocean earthquake in 2004, that really surprised scientists and taught us that we really don't know enough about these subduction zones and the hazard that they pose. And we really have a heck of a lot more to learn. And understanding the potential for these types of events at subduction zones, both in New Zealand and globally, will really help us learn what we need to do to be better prepared when they actually do happen in the future. And then one more slide, Ben, I just wanna, if you're controlling it. Yeah, there we go. I just kind of wanna remind everybody there's been a massive amount of investment from both the New Zealand government and also international science investment in really trying to understand the Hikurangi subduction zone and the hazard that it poses. And the work that's gone on over the last several years has really produced a step change in our understanding of the subduction zone. But there's been a lot of pretty exciting and amazing data sets that, you know, dozens and dozens of people have been collecting over the last few years. And once they work through all that information, I think we're going to be going through another step change in our understanding of the earthquake potential and tsunami potential in the subduction zone. So I just want to acknowledge that there's many, many people working on this problem. So it's going to be interesting times to see what they find in the next few years.
Hey, that's really awesome. Apologies for the technical glitches as we went through there. Just on your last point, Laura, I think it's really cool how much innovation and sort of science has gone into the Hikurangi zone, subduction zone in sort of like the last even 5-10 years, and there's so much that you guys are finding out that you've sort of highlighted in that. So first of all, thank you to the three speakers for such a thorough overview, particularly on what we currently know, but also sort of what we're trying to find out about the Hikurangi subduction zone. And also from Natasha around the earthquake and tsunami risk and how we're planning for that. I'm going to ask questions. The chat box has been going relatively hot, and I'm going to ask some questions. So if you have further questions, just send them through if there's something that you'd like to know. First question, which is interesting. How is tsunami sand different to normal sand? That's something that maybe Kate could talk about.
Yeah, good question. It's where you find it. So tsunami sand is not different, is composed of the sand that you might find offshore of a beach, or the beach sand, or it might be dune sand, but we find it where we shouldn't find it. So we look for tsunami deposits usually in freshwater environments. So we look for them in things like freshwater lagoons, or sort of in the wetland swamps in between dune swales. So they're places that you wouldn't expect to see marine sand. We use a lot of, again, we look at the microfossils in the sand, so we can tell if the sand came from offshore, even in some cases, how many meters deep the sand came from. And so, yeah, it's really the context of where you find the sand. It's all marine sand, but if you find it on land in a freshwater environment, you know it shouldn't be there. And often, one of the only ways to get it there is by a very large wave. And one of the most obvious explanations is that was a tsunami wave, because you can usually rule out that the site is could be reached by a storm wave. Yeah, thanks.
Great answer. The second question, what has been happening in Levin? Why so many earthquakes there?
Laura.
I can answer that, I guess. The earthquakes in Levin have actually been pretty interesting. You know, at first, when they were happening, a lot of people thought that they were actually happening within the subducting Pacific plate. As it goes down, sometimes it distorts, and you can get earthquakes and faults developing within the subducting plate. But some more recent work that some seismologists at GNS have been doing are actually locating them a little bit shallower, actually maybe in the Australian plate, above the subduction plate boundary. So the earthquakes in Levin are not on the subduction plate boundary. They're either in the Australian plate or in the Pacific plate. They're not on the plate boundary itself, but they're happening close to the plate boundary. And one of the other things that people might be wondering about, because where the earthquakes in Levin are happening are very close to where the Manawatu slow slip events happen. They're right at the bottom end of where they happen. And so something we're keeping an eye on is, you know, if those earthquakes might actually trigger the Manawatu slow slip event to happen again. We've seen that in some earthquakes in the past, like the Kaikoura earthquake triggered a lot of slow slip events. And part of the reason we're wondering about this is because the Manawatu slow slip event, it last happened about 4.5 years ago. And so we're expecting the next one to happen pretty soon. So it's sort of almost ready to happen. So keeping an eye on that as well. But yeah, the Levin earthquakes are actually pretty interesting. A lot of scientists at GNS are looking at those right now.
Cool. Third question, possibly for more directed at Laura too, but why does the East Coast get more earthquakes on average in total than the rest of the North Island?
I haven't actually looked at the numbers to know that the East Coast gets more, but the East Coast does get quite a lot of earthquakes really because of the Hikurangi subduction zone. And, you know, in addition to these upper plate faults that Kate mentioned, the subducting Pacific plate, as I mentioned before, it sort of buckles and distorts as it's subducting. And you can often get a lot of earthquakes in the slab there. So a lot of the earthquakes that people have felt, you know, maybe more recently have also been within that subducting Pacific slab. Some of them have been more along the boundary between the Pacific and the Australian plate, along the subduction boundary. But we also do feel quite a lot here. I know in Wellington, I'm not on the East Coast. So I suspect we get, you know, maybe almost as many in Wellington as folks feel on the East Coast as well, but you do get quite a few on the East Coast. But in the North Island, most of the earthquakes we get are really somehow related to the subduction zone, because that's our big plate tectonic engine in the North Island.
Do you have something to add to that, Kate, in terms of why you've selected around these parts for your trenching experiments and that sort of thing?
Yeah, I mean, like Laura said, it's because that's where the plate boundary is. So it's where all the where all the plate tectonic action's happening. The other place in the North Island that's kind of a hotspot for earthquakes is around the volcanic rift areas. So that sort of area from Taupo up to Whakatane has a lot of shallow, small earthquakes as well. Again, that's related to the plate boundary, but yeah, the East Coast sees and feels a lot of earthquakes because of the Hikurangi subduction zone.
Cool, we've got more questions coming in. How can you include slow slip earthquakes into earthquake history that Kate presented?
So how can you include slow slip? Kate, do you want to take a stab at that, or do you want me to?
I can start. And so the slow slip the slow slip that Laura sees, it doesn't, well, first of all, it gets recovered. So you could sort of saw that seesaw pattern in the GPS. So the movement will go one way, and then the intervening period between slow slip, it kind of goes the other way. So the movement kind of is a sawtooth going up and down. So it recovers itself. But I mean, the second thing is that they're just too small to leave a geological record. So no, at the Hikurangi subduction zone, we can't see geological evidence of past slow slip. They're just too small. Yeah. Anything else, Laura?
Yeah, I mean, it would only be maybe a centimeter of movement vertically on the coast, which would be really hard to see. But I mean, another thing to point out is some of the slow slip areas off the East Coast, off Hawke's Bay, where we see a lot of slow slip going on right now. That's also an area where Kate's got really good evidence for past subduction earthquakes. So I think we can't rule out the possibility that these areas that slip in these slow motion earthquakes, I think it's also possible that they can slip in fast slip seismic earthquakes as well, that you know, as we've seen from Kate's work.
Cool. All right, another one. What is different between the Hikurangi subduction zone compared to the Kermadec Trench?
So with the, do you want me to go for that one? Or,
oh, Laura. Yeah.
Yeah. Okay. So, well, what's different? We don't really know very much about the Kermadec Trench. I mean, the Hikurangi subduction zone and the Kermadec Trench are very similar in that they involve subduction of the Pacific Plate beneath the Australian Plate, and they actually, technically, are part of the same plate boundary. They actually connect up and link up. It's a little artificial that we have two different names for them. But the Kermadec Trench is much more of a mystery because it's much more difficult to study because you're mostly under the water. So you don't have a lot of land like we have in the North Island where we can put lots of instruments out and study it. So the Kermadec Trench, we really need to be looking towards new technologies and a lot more extensive technologies to really figure out what's going on up there. But the Kermadec Trench we think it probably does have large earthquake and tsunami potential. It's just not very well understood. And the other interesting thing, you know, is the Hikurangi subduction zone is New Zealand's fastest converging plate boundary. But then if we go up to the Kermadec Trench, the plates are moving together even faster. You know, off East Cape, in the North Island, the Hikurangi is converging at about 6 centimeters a year. But if we go further up the Kermadec Trench, you're looking about 9 or 10 centimeters a year. So things are moving even faster up there. So yeah, so that's a really important area that I think we need to investigate and spend some time studying in the future for sure.
Does that explain why the Kermadec Trench is kind of deeper than the Hikurangi subduction zone? Is it related to the speed or?
It's partly deeper because the Hikurangi subduction zone, part of the reason that we have land above it is because we have a continent the continent is overriding the Pacific Plate that's subducting. And also the Pacific Plate east of the North Island is actually a little thicker than it is further north up the Kermadecs. So further north, you have a thinner oceanic plate and it's a little bit denser and you don't have that continent in the overriding plate. So those two sort of both kind of oceanic plates coming together causes you to have a bit deeper trench up there compared to down here in the North Island and the Hikurangi Trench.
Awesome. Can GPS be used on the seabed?
Yes, we're doing it right now.
Did you write that question, Laura?
Yeah, I did. I must have. We actually have 2 GPS sites running off the Wairarapa coast out near the trench because we want to try and figure out if the plates are locking together all the way out to where the to the trench, to where the seabed, where the plate boundary comes up to the seabed. And then we also have another GPS site off on the seabed off Hawke's Bay. It's really different though from GPS sites that we have on land, because as you can imagine, you can't have an antenna underwater that's going to collect data from GPS satellites. So we have what we call acoustic transponders on the seafloor, and we basically survey them in every year with a wave glider. It's like a remote controlled boat, it's almost the size of a surfboard, and it has a GPS on it, and it's constantly pinging to these transponders on the seafloor and surveying their position in, and it's also collecting data from the satellites at the same time. So we can use all that information to back out the position of those sites to within about a centimeter. So we can look at sort of centimeter level changes in the horizontal movement of the seabed, similar to what we can do on land. Not quite as good of accuracy as we can do it on land, but we can, but it's not bad. It's pretty good.
How do they stay on the seafloor? You know, like how do they not get covered in sand and?
Oh, well, they're out in deep water, so there's not a lot of sedimentation out in deep water. The sedimentation rates out there are very, very low, but they're actually attached to concrete benchmarks that are anchoring them to the seabed. So, and then we can eventually go back and recover them and replace batteries and put them back down. So
that's fascinating. How much larger would a tsunami be from a magnitude 9 earthquake in comparison to a magnitude 8?
Kate, do you want to?
Yeah, I can start. It would definitely be larger, but a lot of it depends on where exactly on the subduction interface the slip occurs. So if you have an earthquake that's quite deep and doesn't go very far towards the shallow part of the subduction zone, then it might not produce a very large tsunami. So it all depends on the amount of slip that you get, basically that moves the seafloor. So on the shallow part of the subduction zone. With a magnitude 9, you're far more likely to get a large amount of slip out near the trench, and you're far more likely to get a large amount of seafloor displacement, so a larger tsunami. But likewise, you could have a magnitude 8 earthquake that's predominantly out towards the trench, so it will also produce a really large tsunami. So yeah, I would say in general, I can't precisely say exactly how much larger a magnitude 9 earthquake would produce in terms of a tsunami than a magnitude 8, because yeah, it depends on where that rupture occurs.
And depth and various other things.
Yeah.
Another one to point out is the 1947 earthquakes that Kate mentioned. They were only magnitude 7.2 off Gisborne, and they actually caused, you know, like 8-10 meter tsunami, which is a lot bigger than what you'd expect for a magnitude 7. So as Kate said, it very much depends on the details of where these things are happening and how much seabed displacement they cause.
Yeah, that's one of the reasons why we try and look so hard for these tsunami sands, because we don't have a very good understanding of how large the tsunami will be produced by one of these subduction earthquakes. So yeah, that's why looking for tsunami deposits is quite important for our geology research.
I guess that links to another question for you, Kate, in terms of is there evidence of a past tsunami from the Hikurangi subduction zone on the Chatham Islands? Have you done any research out there to see, you know, things moving?
Good question. We've written a proposal to try and do that. There has been quite a lot of tsunami research on the Chatham Islands because they are very exposed to tsunamis from a number of sources. So they are particularly vulnerable to tsunamis that come from South America. So at the moment, we don't know of a tsunami deposit out on the Chatham Islands that is directly related to a Hikurangi subduction zone earthquake. But we would like to go, we do know that there are significant tsunami deposits out there, including an area where lots of boulders have been picked up and moved by tsunamis. So we would like to go out there and do some more precise dating of those tsunami deposits and see if they correlate either with tsunamis that come all the way from South America or tsunamis that have come from the Hikurangi subduction zone.
Interesting. Laura, Are slow slip earthquakes helping to reduce potential of larger quakes around Gisborne?
Yeah, so the slow slip events, because they're happening so often and they do appear to be accommodating, at least for the last 15 years or so, most of the plate motion between the Australian plate and the Pacific plate. Probably overall, like over the long term, they're probably reducing, the number of really large earthquakes, like magnitude 8 earthquakes that might happen. But I think there's still, a lot of potential in the Gisborne region for smaller earthquake, like the 1947, the magnitude 7.2 earthquakes that actually caused quite large tsunami. There's still, I think, quite a lot of potential for those happening. There's parts of the plate boundary around Gisborne, some smaller parts of the plate boundary that are locking up there. They don't completely remove that potential, but over the longer term and for the really big earthquakes, I think, they do reduce the number of really big earthquakes required to accommodate the plate motion up there. But yeah, I think you still have earthquakes and tsunami, unfortunately, in Gisborne.
Yeah.
Everywhere along the East Coast, we have to be prepared for that.
And there was the sort of, after the Canterbury quake, there was the shifting of the kind of energy up here with slow slip and things being triggered by that, wasn't there? Or Kaikoura.
Or the Kaikoura earthquake. Yeah, that was sort of mind-blowing, actually. I've never seen anything like that. The Kaikoura earthquake triggered slow slip events in the Kapiti slow slip area, and then all up the East Coast from East Cape all the way down to Parangaho and southern Hawke's Bay. Was triggered by the Kaikoura earthquake. And there was actually off of Parangaho a magnitude 6.1 earthquake on the subduction plate boundary that happened during that slow slip event that was triggered by Kaikoura. That was probably the best example that we've ever seen in the world of really large scale triggering of a slow slip event by an earthquake, by a more distant earthquake, a regional earthquake.
Cool. I've got a question from close to my home here in Napier, and it's, are the hills west of Napier being compressed and pushed? Not quite sure. Yeah.
The hills west of Napier.
Taradale Hills, yeah.
They're referring to the low hills, sort of in behind Taradale, or the axial ranges like the Kawikas and the Ruahinis. In general, most things along the Hikurangi subduction zone, most hills are being compressed and pushed up. So, yeah, by forces deep and shallow. So, yes. Yeah. Once you get further over towards the axial ranges, those big mountain ranges, there's other upper plate faults that come into play. So things like the Ruahine fault and the Mohaka fault, they're quite significant strike slip faults that move sideways, but they do also produce a bit of compression and vertical movement.
So Kate, wasn't the 1931, that earthquake, that caused a lot of uplift kind of through Napier in that area, and there was probably the reverse component of kind of bit of compressional component?
Yeah, 1931 was on what we call a blind reverse fault, so a fault kind of buried underground, and that was a reverse fault, so that involved compression between the two sides and uplift. Yeah, they are being compressed and uplifted, and it's all driven by this collision between the two plates.
Cool. I've got a few more questions, so I'm going to up the ante, and we'll be awful if Natasha left this evening being question free. So I've got one for her. In the Bay of Plenty, does the coastal orientation mean there will be less of a tsunami impact on us?
Oh, I think that one might be a little bit more for Kate or Laura, I would say, but if they're not sure.
I can say a little bit about the Kermadec Trench. If we had earthquakes on the Kermadec Trench, which is that northern continuation of the Hikurangi subduction zone, that could potentially cause, pretty large impacts in the Bay of Plenty region. So not immune to tsunami impacts from the subduction zone. I think if it was, you probably would have less of a tsunami up there if it was, say, just a subduction earthquake in the southern part of the North Island. You probably wouldn't have so much, but the Kermadec Trench and subduction earthquakes happening off East Cape in that area could certainly generate tsunami in the Bay of Plenty, I think. Kate, do you have any?
No, I think that about covers it. Yeah, it does depend in terms of shelter from a Hikurangi subduction zone earthquake. It does depend on where on the Hikurangi subduction zone it occurs. If it's a more northern earthquake that occurs, say, up near Gisborne or further north towards East Cape, then the Bay of Plenty is not really sheltered from that. I guess the other thing is that within the Bay of Plenty, offshore, there's still a lot of active faults. There's smaller faults, but they are still capable of producing a local tsunami there.
So this might be a question or similar questions to revisit with William Power next week. He might be able to clarify a few of these points.
Yeah, you guys will have a tsunami expert, and William, Kate, and I are just trying to be.
Oh, you gave pretty jolly good answers, so we're not going to hold you over the barrel for it.
And then actually, in terms of different locations of earthquakes on the Hikurangi subduction zone, we probably will touch on that next week when we talk about the response planning project, where we looked at a range of scenarios that could occur, because of course there's thousands of different scenarios that could occur in the future, and we can go over that then and definitely address any questions around that.
Awesome. A quick question. Did we find the missing sensors that went adrift last year?
Kate, why don't you answer that? I guess that's for me. So we put out, for people that don't know, back in late 2018, we put about 30 seafloor sensors out to measure earthquakes offshore the East Coast, off Hawke's Bay and Gisborne, and then also pressure sensors to measure up and down movement of the seafloor during these slow slip events. And so most of our instruments came back, but there were a few that we couldn't actually hear from, and we went back to retrieve them a year later. And so we put out the word for people to have a look for them, when they're on the beach. If they see, they're basically about the size of a washing machine, and they have these big yellow floats on the side. I think you would notice them if you ran across it. But we haven't had anybody report them having washed up on the coast. So I suspect they're probably still on the seafloor. Maybe they're the acoustic, the transponder that we use to talk to the instrument, maybe it malfunctioned. And they're probably, hopefully they're sitting there on the seafloor and collecting data. We're not sure, but we're hoping to get an underwater robot, a remote controlled robot called Jason, from the States to come over here and have a little rescue mission and look and see, hopefully, if we can find them, if we have some time with Jason to do that. So we're going to go and have a look, try and get them, because they have some really important data, because those sensors were sitting right above a really big slow slip event that we had off offshore Hawke's Bay last April, May last year. So we'd really love that data.
Awesome. So just final two questions before we finish up. Is there any evidence of tsunami on the Wellington Coast outside or inside the harbour? Interesting question. Kate, for you.
There is evidence of tsunamis just on the other side of Cook Strait, over at the Wairau Lagoons near Blenheim. And we have seen evidence of tsunamis at Okupe Lagoon at the northern end of Kapiti Island. We haven't seen a lot of evidence for tsunamis around the Wellington Harbour and outside of Wellington, but this is probably not a signal that they haven't impacted the areas. First of all, it's quite highly developed. So to do our research, we generally need undisturbed coastal landscapes. So there's very few places that we can actually look that haven't been impacted by human development. And then the places that haven't been impacted by human development are the really rocky, rugged coastlines. And they're not very good for tsunami studies, because as you can imagine, if you get a tsunami on those coastlines, they might pick up a few rocks and a bit of seaweed and then deposit it on a rocky beach. And they're just not very sensitive environments for recording tsunamis. So unfortunately, the Wellington area is obviously would really like to know more about tsunamis, but the coastal environment's just not very suitable for tsunami research.
Hey, do you remember what happened in 1855 in terms of tsunami?
I wasn't alive then, Laura.
Well, I thought you were.
Not that old. So 1855, there are lots of historic documents. The tsunami from that, so 1855 was a magnitude 8.2 earthquake on the Wairarapa Fault. It uplifted Te Hickory Head by almost 6 meters, and it generated a tsunami that was up to 11 meters high in Palliser Bay, and a tsunami large enough to it crossed that sort of isthmus between Miramar Peninsula and the mainland, so across where the airport is now.
Where the airport is.
Yeah, so it was quite a significant tsunami, but nobody has ever found the sort of geological record of that. I mean, in the Wellington area, that, yeah, you know, there's been so much development around the port and the wharf and where the airport is, so any evidence of that's probably gone. And people have looked a little bit over in Palliser Bay for evidence of that tsunami, but we haven't successfully found it yet, although we haven't put in a major effort to do that. Yeah.
Cool. All right. One final question. We clearly have an aspirational scientist out there. What is your best advice for someone considering a career in science?
Kate, do you want to go first?
Study hard.
For somebody's, I don't know. I would say take science classes in school, and definitely mathematics classes. Doing your maths is really important, and then getting to university and probably exploring a range of sciences, especially earth science and geology. You don't really get exposed to a lot of that in school, in high school in New Zealand. So yeah, I would say in the first year of university, take a few different types of science and see what is really of interest to you. Yeah. Laura?
I would say if you find the science or find the subject that you love, because if you love doing it, then you're going to be really willing to work your butt off, because that it's a lot of hard work, but it's totally worth it and really fun. So find the science that sort of sparks your passion the most, the subject that sparks you the most.
Awesome. All right, so we'll wrap up. That's all we have time for this evening. Thanks so much, Laura and Kate, for your brilliant insights, and also Natasha for your lovely presentation to start us off. There'll be a second talk next week, Thursday, 11th of June at 7 p.m. Same time, same place, just a week later. Make sure you encourage all your family and friends to get involved. The more the merrier. So thanks very much for coming out and checking us out this evening. If you want to learn more, there's some resources here that you can find on YouTube, GNS and various other resources that particularly Laura taking a cameo up in the top left, along with Kate and various other ones of those. And yeah, you can find more info at Get Ready and East Coast Lab on our website, social media, and our new Instagram. Please follow us there. Just a quick note, apologies for the spam links that were coming up on this feed. I didn't realize we were so popular from spammers wherever they're hiding out. But yeah, until next week, haere rā, and thanks for coming.